next exercise, which you can see here, we're still concerned with everything about divergence, rotation, and gradient. But this time, the focus is on a given vector field instead of a corresponding potential. Much the opposite in comparison to the previous one. I will explain. So the following spatial vector field, spatial always means three-dimensional, is given, and it strikes you that it doesn't look as simple as the previous one on the one hand, but on the other hand, it seems to have certain similarity. If you remember, our previous field was simply 2 times the radius vector itself, so it was something like x, y, z. We still have x, y, z inside the corresponding components, but we have an additional factor of x. This makes this field relatively, I could say perfectly appropriate to explain the, yes, another or even 2 more general correspondences between rotation, gradient, and divergence. Well, we'll find out. And I can tell you now that it's quite probable, at least by looking here, that this vector field will have a certain divergence, at least somewhere in space, and also a certain rotation. So this is sort of a mixed case of divergent and vortex field. A vortex field, but not a pure vortex field. We'll find out mathematically. So first of all, find out, or even, well, just find out whether this is a gradient field. Now, I already told you quite surely it can't be a gradient field because it seems to have rotation. This is due to the fact that the x variable appears everywhere. And okay, this is just a matter of experience to see this with blank eyes. But imagine, or two possibilities. Either the rotation is the null field, it's 0 everywhere, or it is not. In any case, there is a certain method of trying and finding a valid potential. Because you see, after we perhaps just guess, is this a gradient field, yes or no? If we say yes, it is, we have to be able to find an according potential by calculation. If not, we have to prove so. Okay, and then secondly, the divergence and curl, or let's say rotation, are to be calculated. And then some interesting combinations, which are divergence of rotation of f of x, then it gets really abstract to imagine what might this be, okay? And this is, for shortness, I abbreviated the rotation of f to be called capital R. You see what I mean? So, because this is also a vector field, and this transformed vector field, rotation of f, will be called R, capital R vector of x. And then we also want to know the divergence of this, and then even the rotation of this rotation field. I think for my own, well, way of dealing with abstractions, this is the most abstract thing in this whole context. To imagine what does the rotation field of another vector field mean. You don't need to understand it in so much depth. You may try, but it's quite interesting which properties hold for the rotation of another rotation. Okay, we'll see. First one. Question: is the vector field f a conservative field? In other words, does it have a valid potential? The answer is no. I already stated that, but I want to prove it. Well, this is not really a clean proof, but it's sort of quite a straightforward method to simply find out. And I hope you can easily understand what I'm doing here. I'm doing the following. Since I know, and as I told you before, that at the moment it's unknown, but our unknown potential, which we are looking for, if it exists, it must be the primitive function of this vector field in a certain sense, in the sense of taking the gradient backwards. And taking the gradients, is that true what I'm saying? Yes, because now the problem is, it might well be that this vector field is the gradient of an unknown potential, but here it doesn't help to take the gradient of something because we don't have the something. So we must sort of take the inverse gradient. And now remember what the gradient is. I just jump back for a second. The gradient is to take the corresponding partial derivatives of always the same scalar field. That's important. And so now what we have to do is, now imagine this were our vector field, also here it holds, we would have to take the primitive of this one corresponding to x, of this one corresponding to y, and of this one corresponding to z. And every time we should get the same expression. And as you see, this is more or less the only possible function of three independent variables which holds this condition, which fulfills this condition that its partial derivative for x equals 2x, for y equals 2y, and for z equals 2z. And analogously, we have to try and do what I just told. So we will try and integrate indefinitely, okay? So this is an indefinite integral. We will try and find the primitive function of x squared simply, because x squared is the first component of the vector field. Just do so. So you may know that, well, the notation with the integral sign and the differential, the x, this is really the original notation introduced by Gottfried Wilhelm Leibniz when he and Newton independently, you could say introduced differential and integral calculus. So what I want to say here is it has historical reasons that we never introduced a special notation for really partial integrals. You know what I mean? Because I should say this is not a regular integral. Instead, this is an integral just exclusively with respect to x and not with respect to y and z. So there could be a special sign for taking sort of the inverse of a partial derivative. So that's what we're doing here. Okay, exactly. We are taking the inverse partial derivative. And then we have to find out, or we try to find out perhaps, that this is why I put a question mark here. Is it possible that the result is identical to the second field component integrated for y and also the third component integrated for z? So you could say this is the challenge now, to find terms which are compatible with each other in this respect. Okay, so let's do it. X squared, just now a little faster perhaps if possible. X squared primitive equals 1/3 x power 3. We all know that. But now there's an important detail. This is an indefinite integral, which means that I have to allow for an integration constant, which I call C1. And now you will be perhaps a little bit confused for a second, because when I say this is a constant, at the same time, I give it two arguments, which are y and z. And so in a certain sense, it's also a function or a term. Well, for a simple reason. When I say this is a constant, which must be allowed in an indefinite integral, what I mean is it's a constant with respect to variable x. So we all know what it's about. The task is to find the most general term which has a partial x derivative equal to x squared. You know what I mean? Just take the partial derivative of this one for x. Well, here the derivative will be 3/3 times x squared, which is x squared. But here we have an additive term which does not depend on x. And because it does not depend on x, it must be allowed. Since when I take the partial derivative for x, it just disappears. Now you got it, right? So you see, this is the most general result for this integral. Now here, it will be different because xy, yet this time integrated for y, or with respect to y. This is just a tongue breaker, because that's why I always avoid saying with respect to. I tend to say for. I hope you got it meanwhile. Well, y integrated for y, of course, is 1/2 y squared, but the factor of x, which is not, which we leave alone, is it just stays there. So that's it, 1/2 x y squared. And for the same reason as before, I must allow for another integration constant, which this time, constant in quotation marks, this time it may depend on x and z, but it must not depend on y. So it must be independent from y, and that's what it is in this way. Check it, you just take the partial derivative for y, this disappears, this one gets you 2/2 xy, so it's x times y in the end. Everything's fine. Next and last one, final one, x times z integrated for z. It's quite similar. You get 1/2, x stays there, and then z squared, and plus a third constant, which may depend on x and y, but not on z. Now, this is not everything. It's not done yet. At first sight, you will note that these terms are so different that they don't seem to be the same. But now, in many other cases, we would succeed. We would succeed finding a corresponding potential y, because we still have 3 degrees of freedom. Now we can adjust these still unknown terms of this one of y and z, this one of x and z, this one of x and y. We could adjust them in a certain way, so that in the end we have one big term which fulfills all the conditions. This is the good idea behind. The bad news is we will not succeed this time, because it's just impossible. Now look, this is the idea. I say if we find a potential phi of x which fulfills all the conditions, it must at least contain this term. It must contain this term. It must contain this term, because these are the terms which get you the needed results as components of the vector field. But it may also contain another additional, these other additional constants. Now, do you see what I'm doing? I say this and this. These two elements are contradictions to our preconditions. A little hard to say, to explain. Yeah, I can show you. The whole term in the end, even without any additional constant, must fulfill the structure that we found before. So this whole term must fulfill that it contains 1/3 x cubed, which it does, but everything else must be constantly, not additively dependent on y and z, never on x. There must not be any other element inside here which depends on x. For a simple reason, because now it's easy also to check it. Take this term and now take the partial derivative for x. So you get your x squared, which you need here to be the first component of the vector field, but you would also get, differentiating this one for x, you would also get the factor of 1/2 y squared. And 1/2 times y squared is not inside the first component of the vector field. So this is a contradiction. And the same thing holds here, because, well, that's even enough. Well, I can argue, how is it? Okay, yeah, here, because this term is needed, it's there, we put it there, but everything else must only depend on x and z from this perspective. So, okay, this one, fine, depends on x and z. This one depends on x only. And so in the end, it means for the y component, for the second component of the vector field, there's no problem at all. We have a problem, as we saw with the x referring to the first f component, and we also have a problem referring to the third. I can show you also, because this term must be there. Here it is, but all the rest must only depend on x and y and not on z. Actually, now I see I made sort of. I must. Oh, it does. Actually, it doesn't now. Now I know what I wanted to tell you. Sorry for the little hang up. Well, actually, it works well for the second and for the third component, but for the first component of the field, we have two contradictions. That's what I wanted to say, right? So let me repeat this. For the first one, we get this 1/3 x cubed as we want. everything else must not depend on x, but it does depend on x here, not only here, but also here. So that's why I have two contradictions even. Again, if I take the partial derivative of this one for x, I get my x squared, but I also get my 1/2 times y squared and even plus 1/2 times z squared. So this is sort of two contradictions referring to the first vector field component. The other two, no problem. I can show you, because now, just for testing, let's take the partial derivative for y of the whole term. So this disappears because it does not depend on y. This disappears, it does not depend on y, but this one gets us 2/2 xy and in the end xy. And even here it would work. The z component, partial z component of this potential will be 0 here, 0 here, no dependence on z. And here the result will be 2/2 x times z. So that will go fine. In the end, the vector field, which would be the gradient of this potential, as we now found out, would look like x squared, what did I say? Plus, well, y squared half in the end, right? Differentiating for x now, like this. And then even z squared half. You see what I mean? The other two components are absolutely fine. So this is the possible vector field. And this vector field actually is a gradient field, and it is conservative, but it's not identical with this one. And this one does not lead us to any valid potential. I'm sorry for the little complicated explanation, but it's done. Okay, so we clearly showed that f of x, that let's say there does not exist any potential phi of x vector, so that f vector of x vector equals gradient of phi of x vector. So that's it. Now to the second, or for the second part. Again, we want to see what is divergence and rotation of this field. Now, this is not very surprising or not even complicated. Well, let's always look here or keep in mind, this is our field. Can you keep it in mind? It's just like x, y, z, but additionally multiplied with x. So we have x squared, xy, xz, easy to be remembered. And now let's do it in our mind, namely, divergence. Remember, it's the scalar product of the nabla vector with the field vector. It means we have to take f1 partial for x plus f2 partial for y plus f3 partial for z. So what is it? X squared differentiated for x gets you 2x. This one is, the second component is x times y. Differentiating for y gets us an x, so plus x. And thirdly, x times z differentiated for z, again, gets us a contribution of plus x. Remember that the divergence is not, itself, it's a scalar field. Important, right? That you can say the feature or the attribute of being divergent, this is a field attribute, an attribute of a vector field, and this attribute is not, it's non-directional. You must understand, it is a signed quantity. So divergence you may find three different cases. One of them is, we are talking of a so-called flux. That's an important term, which will come up shortly. The flux of a vector field describes whether, going back to the picture of streaming fluids or gases, whether a given vector field points outward of a certain closed surface or inward, or neither nor, right? So if the flux is positive, you have at this position in space, you have a tendency of this vector field to the field vectors to point outward from some starting point, right? If it gets negative, it points inward. I will not make a drawing now, but you can imagine. And if it's 0, which is often the case, you can interpret as to be a flow through a closed surface, right? So this would mean that for a given little closed surface, there is some streaming outward, there is some streaming inward, or there's some streaming through. These are the three cases. And that's interesting because this corresponds to the sign of the local property, which is called divergence. The flux is more here you see it. It's more like something macroscopic. Okay, you can say divergence is a microscopic feature of a vector field, while the flux is macroscopic, and to calculate it, you often perform a two-dimensional so-called surface integral. Better speaking, a closed surface integral, which we sometimes also call a hull integral. You know, hull as a closed surface of some volume in space. So these are the many connections between all these operations. Now, what do we get? We get 2x plus x, which is 4x in the end. And this is quite surely not identical to 0. You know, these three bars, this is a certain way of saying not everywhere 0, okay? Well, if I take this away, something like this is sometimes used to say this is not 0 by chance, but it's 0 everywhere and anywhere for any value of x. But as you see, this is not the case, okay? For x may be 0, especially if x itself equals 0. So, but this allows me to take this notation. And I want to say that all I want to say with this notation is that this is not the null field. This is not the null field. It's a field which is more than a null field. It's there, okay? And it's quite strong even. So our vector field has a relatively strong and growing so-called divergence if you go away from 0 along the x-axis. That's an interesting property. It's just a fact that this, well, the divergence and the flux of this vector field, it grows in x direction, and also it goes to negative values on the negative half of the x-axis, of course, but this holds for any for the whole space just regarding the x position. So there's no dependency on y and z position. It's quite a special kind of flux, you could say. Okay, radiality, a sort of radiality, but this is not a purely radial field. Of course, it's not spherically symmetric in a radial sense. Not at all. If it were, it would have a 0 rotation, but it doesn't. It has a non-zero divergence and a non-zero rotation. That's what makes it interesting. Okay, let's proceed. And we see the rotation, yet now called capital R vector. Short notation, I'm not always writing field vector of x vector and so on. Well, but the rotation of this vector field F equals, same procedure as before, taking the vector product of nabla and field F. Well, I won't explain it again. You know where it comes from. We have to take F3 partial for y minus F second partial for z. Here, F first component partial for z minus vice versa. Here, second for x minus vice versa means, okay, you know what I mean. The second one for x, the first one for y. Okay, that's well known. And that's interesting. Here you see it again, just to remember. Let's do it in detail. What is the third component differentiated for y? Well, it doesn't depend on y, so we get 0. Minus the second for z. The second does not depend on z, so 0 again, it's 0. This is not a surprise. It just says that the, let's say, the axis around which the vortices of this field exist has no x component. It has just a y, possibly a y and a z component. You may immediately see this with blank eyes looking at the structure of this field, or if not, it's no problem now. Okay, the second, so first component, partial derivative with respect to z, as always. So the first one does not depend on z, so nothing again, but minus the third one differentiated for x. So the first time we have a dependency, you could say a foreign dependency, right? Because the third component depends on the first coordinate. And that's why we get a contribution. Well, the third, this one, differentiated for x, equals z, but we have a minus sign inside here. So negative z is the result. And also the second differentiated for x here, it does depend on x, and the result is y. The factor y stays there. So that's the result. And then again, minus the first differentiated for y, there's no dependence. So that's all. We get 0, negative z, y. That's an interesting rotation field itself. It's not identical to 0. So again, it holds, it may be 0, but only, to be honest, when y and z are 0, which you know what it means. Actually, it means that you are on the x-axis. So the rotation of our vector field f from above, this one, is non-zero almost everywhere except for along the x-axis. You see why it is? It's quite simple. Or is it? Well, sort of. We could argue the following way: if y and z are 0, also the second and third component here gets 0, and then so this field has no vorticity anymore, because it can't have vorticity if it points in one and the same direction with, along the x-axis. Even if it's growing along the x-axis, there's no vorticity at all. The vorticity gets lost as soon as you find yourself along the x-axis. So that's not really surprising, but there's more important things to find. So we take our resume and say, or resume, there is vorticity, there's also flux. So this is a mixture between a radial and a vortex field. That's interestingly, as complicated as vector fields may be in their behavior, you can really say everything can be described as a combination of radiality and vorticity, actually. Okay, that was the second, and I will shortly complete it with the third part.